Hey everyone, welcome. Today we're working on a very difficult problem that's called sum of square. So this question, sum of square, is the February 2024 Jane Street Challenge, and it goes like this. So a circle is generated by sampling 2 points uniformly and independently from the interior of a square, and using these points to determine its diameter. So we choose 2 points like the red point and blue point here, and we use that to determine the diameter of a circle. So we choose 2 points like in the example 1 here, and we would draw a circle using that as the diameter. So we want to determine the probability that the circle has a part of it that is off the square or outside of the square. So in this case, we can see that there's 2 parts of the circle, the top part and the right part. Both of those are off the square. So what's the probability that the circle has a part that's off the square, and give your answer in exact terms. So we don't want the answer in a decimal, we want it in terms of an actual number or fraction. So how should we do this? First of all, let's draw a square. And let's call this 0. It has a side length of 1. So this question wants us to generate 2 points uniformly and independently to form a circle. But that's very hard for us to take advantage of the two points and do an integral based on them. So instead, we're going to transform the problem statement into something that's easier for us to work with and something that we can actually integrate. So instead of choosing these 2 points, let's say we choose something else. Let's say we choose the center of the circle. So let's call that point C with coordinates x, y, and we choose another point P. Let's say this point is point P. So to determine the other point that the question wanted us to choose, we're going to take the distance from P to C and reflect it across C. And this way, we get the other point the question wanted us to choose, the point Q. But notice this way, Q is actually off the square. And the question doesn't want us to generate a point that is off the square because the 2 points are uniformly and independently on the interior of the square. It's on the interior. So sometimes using this new sampling method, we're going to generate a point that is off the square. So we want to determine what the chance is that we actually generate a point that's off the square because we don't want that. So looking at this square here, we know that C has coordinates of x and y. So let's draw a dotted line. And this distance here from 0 to C is going to be x, and this distance here is going to be y. So for P, or for Q to be off the square, we're picking a P that is too large on the x-axis. So how do we determine it's too large? Well, it's larger than 2 times x. So this distance, this is also x, but P is actually outside of this. This is P's x. So that's why it leads to a point Q when mirrored across C to be on the negative of the x-axis, or to be a point that's off the square. So whenever we have a point when a point C for the center, we can draw this vertical line here that represents 2x. So this is the line at 2x. So any point on the left side of this line, so any side in this shaded region, this is not going to result in a Q that's outside. Otherwise, on the right side of this shaded region, it's going to result in point Q being outside. So similarly, we can do the same thing for y here. So like this. This is also y. We can draw a horizontal line here. If point P is too large on the y-axis, so if point P is here, that would result in a point Q that's way too negative. So we don't want that, so we want our point P to be on the bottom of this horizontal line. So now we want to determine what the probability that point P is in this quadrant that's fenced off by the 2 lines. As C goes from 0 to 1 and on the x-axis and 0 to 1 on the y-axis, because x and y are randomly and uniformly distributed, so is C. So we note that this vertical line, as C goes from 0 to 0.5, so C goes from 0 to 1 over 2, this vertical line is going to go from 0, let's call that VL vertical line, is going to go uniformly from 0 all the way to 1. So because we're going uniformly from 0 to 1, the chance that p is on either side of this vertical line is going to be 1 over 2, since we're going uniformly. And suppose we have c going from 1 to 1 over 2, so going the other direction, then the vertical line is going to go from 1 to 0 the other way. And since it's also going uniformly, then there's a same chance that p is on the left side or the right side of the vertical line. So there's a 1 over 2 chance that p is generated, which results in a q that is outside of the square. So this is the same for the horizontal line because it's symmetrical. So there's also a 1 over 2 chance that p is generated so that q is off the square the other way. So like q is 2 negative and q is somewhere like that. So 1 over 2 times 1 over 2 is 1 over 4. So there's a 1 over 4 chance that what we generate is actually inside the square, because if the point P is inside this shaded area, then we have it inside the square. So there's only a 1 over 4 chance that using this new method of picking the center and a point P to generate the circle, there's actually only a 1 over 4 chance that it's actually valid. So what does this 1 over 4 actually tell us? Let's clean this up first. So this 1 over 4 tells us that it's actually 4 times as likely, given whatever probability we solve for later, that the circle is actually inside the square. And why is it 4 times as likely? Because whenever we have a point Q that is outside of the square, that means the circle generated correspondingly, for example, this circle is guaranteed to be outside of the square because Q is outside of the square. So if we eliminate 3/4 of the chances that Q is outside of the square, then we're left with 4 times the probability that the circle is actually inside of the square. So whatever probability we solve for later, we're going to have to multiply that by 4. So now how do we determine the probability that the circle is actually inside of the square? So let's draw a new clean diagram here. And let's make that larger. So we have a square. It goes from 0 to 1, 0 to 1. So now we want to choose a point C and a point P. So this is going to be C, that's going to be P. So instead of choosing the point C from anywhere in the square, we want to do something that's easier to integrate. So because the square can be divided uniformly into 8 different areas, like this, so we can divide the square into 8 different triangles using this method. Let's suppose C is in one of the triangles. So because C only has a 1 in 8 chance of being in one of the triangles, we need to multiply by whatever answer we get later by 8. So suppose C is in this triangle on the bottom left here. And we have, so let's actually shade this so it's a bit more clear. Suppose we determine C to be inside of this blue shaded triangle. Of course, it can be any of the triangles. We're just multiplying our answer by 8 later because it's all symmetrical. So what is the probability that we pick a point P which results in a circle that's fully inside the square? So let's say we have point P here. So the circle would look something like this, and it would be inside of the square. But what's the probability this P actually generates a circle that's inside the square? Well, we can form a circle around C from C to its nearest axis, which is going to be the x-axis. So this is going to be a length of y. So let's draw a circle with radius y that's revolving around C. So something like this circle right here. So notice that any point P, which is inside of the circle, would result in a smaller circle than this, and that circle would be inside of the square completely. Any point P that is outside would result in a bigger circle than this, and that circle would be outside of the square. So we wanted the circle to be inside of the square. So let's actually shade this circle. Let's shade it orange. Oops. So let's shade this circle orange here. And we want the probability of choosing a P so that it's inside this orange circle. Because being in this orange circle means the circle generated will be inside of the square. So what's the probability we choose something, a point P, that's inside the orange circle? Well, it's the area of the orange circle divided by the area of the entire square, because P has to be inside the big square. So the area of this orange circle is pi times y squared. That's the area formula for the area of a circle. But we don't just want pi y squared. We want this for all the c's as c goes from 0 to 1 over 2. For all y's, so for all x's from 0 to 1 over 2, and for all y's from 0 to x. We're saying 0 to x because this line here has a slope of 1 and has an equation of y equals to x. So we're doing a double integral as the x-coordinate of c goes from 0 to 1 over 2, and as the y-coordinate goes from 0 to x. So this is going to form a double integral of pi y squared. So y goes from 0 to x, so dy, and x goes from 0 to 1/2, dx. Let's move this over a bit. So how do we solve this integral here? Well, first let's take the constant out, so take pi out. Now let's do the inside integral first. So the integral goes y squared. So to integrate that, we get y cubed over 3. And this is going from 0 to x. Outside of that is dx. So to expand that, this is going to be x cubed over 3. Oops, I can't write my 3's today. Minus 0 cubed over 3. This thing is just nothing. We can erase it and take dx. Now let's move the 1 over 3 out. So it's 8 over 3 pi times the integral of 0 to 1 over 2 x cubed dx. So to expand that, this is going to be 8 over 3 pi times, this is going to be x to the power of 4 over 4, and it goes from 0 to 1 over 2. So expanding this here out, it's going to be 8 over 3 pi times x to the 4, 1 over 2 to the 4 is 1 over 16, divide by 4 again, that's 1 over 64. So 1 over 64 minus 0, that's going to be 1 over 64. So 8 over 3 pi times 1 over 64, this is equal to pi over 24. So this is our fraction here. This is the probability that we choose a point P for any point C inside the square and any point P inside the square, that the circle formed by the center and this point P is actually inside the square. So remember we said that we want our answer, any probability that we get later, to be multiplied by 4, because it's actually 4 times as likely since we're generating a lot of points Q that are outside of the square. So we multiply this answer here by 4, which gives us an answer of pi over 6. So this pi over 6 is the probability the circle is inside of the square. Now the question doesn't ask us the probability the circle is inside the square, it actually asks us the opposite of that. So what's the probability the circle has a part of it that's off the square? So to get the probability the circle is off the square, all we have to do is take the complement of this. So our answer is going to be 1 minus pi over 6. So that's the answer to this question here. So to solve this question, we first transformed the way the question actually generates the points to a way that's easier for us to integrate. And along with that, we changed the probability and we had to keep a factor of 4 because it's 4 times as likely to generate points that are off the square with this new method. So we have to multiply the answer by 4 to match that. And that generates a probability of pi over 6 that the circle is in the square. Taking the complement of that, we get an answer of 1 minus pi over 6. So that's it for this question. Thank you guys so much for watching. Hope you're able to learn something, and I'll see you in the next video.